Alright, so in this video we're going to talk about systems of differential equations, but now we're going to perform a more general definition of the topic, and we're going to use matrices. So I recommend that you do some revision of linear algebra before watching this video, because we're going to be using some techniques such as getting the determinant of a matrix and then using row reduction to get eigenvalues and eigenvectors. So the idea is that we can have a system of first order differential equations, and I'm going to represent it as x dot, so that's the first derivative, and it is actually going to be a vector. So the vector is going to be denoted by that squiggly line at the bottom, and this is going to be equal to some matrix A, so that's going to be a square matrix, times the solutions, which is going to be another vector. So you may have something like this. Let's say you have a bunch of derivatives, so x1, x2, so those are the first derivatives, and they're going to be equal to something like 3 minus 2 1 5 times the vector of solutions, which is x1 and x2. And now basically what this represents is a system. So if we expand this out by using matrix multiplication, we will find that x1 is going to be equal to 3x1 minus 2x2, and then x dot 2 is going to be equal to x1 plus 5x2. And this is a system of coupled differential equations that we have here, and they're both first order. So in the previous video we saw how we could actually solve this by using a method of just solving simultaneous equations by using some algebraic manipulation with differential operators in it. But we can also solve it by setting up a matrix equation like this, and then what we're going to do is we're going to find the eigenvalues and eigenvectors of this matrix. Excuse me. So we're going to find the eigenvalues and eigenvectors. So in the end, we should end up with a vector of solutions as a function of time that is going to have the following form. We're going to have C1, which is going to be a constant, times the first eigenvector, times e to the power of eigenvalue 1 times t, plus C2 eigenvector 2 times e to the power of lambda 2, which is the eigenvalue, the second eigenvalue, times t. So this is the general form of a solution to a system of first order differential equations like this. And we can also extend this to further cases. So let's say, for example, that we had a system of 3 differential equations. So x1, x dot 2, x dot 3 equals to some matrix, and we're going to have 9 elements in it. So it has to be a square matrix, otherwise this method wouldn't work. x1, x2, x3. So what do you think is going to be the general solution to this system? Well, the general solution to this system is going to be the following. So it's going to be C1 eigenvector 1 e to the lambda 1 t plus C2 eigenvector 2 to the power of lambda 2 t, and finally C3 eigenvector 3 to the power of e lambda 3t. So it is just going to be a linear superposition, and if you can keep going and going with this, so the most general case for a system of n ODEs, we're going to have the following general solution. So the vector of solutions is going to be equal to the sum. So I'm just going to use j as the subscript here, so that's going to be j equals to 1 all the way to n. We're going to have a constant, so that's going to be Cj, and this is going to be eigenvector j, and this is going to be e to the power of lambda j t. So this is the general solution to a system of n ordinary differential equations. Now, of course, they should all be first order. Otherwise, we wouldn't be able to group them into matrices like we did here. And why is that? Well, if you consider this vector, x dot t is just this vector, so that means that, and each eigenvector is going to contain the same number of elements as this. So by looking at each row, you can find each of those solutions. So for example, the solution to x1 would be the first row. So it would be this times the first element of this eigenvector times this, plus C2 times the first element of eigenvector times this, and so on and so on. So that's the general idea behind this. So I'm going to show you an example, and this applies for all kinds of eigenvalues. So you know that with eigenvalues, you can either get real numbers or you can get complex numbers. This applies to both cases. If you get a complex number, you just put the complex number in here as if it were any other number. And that's the beauty of this method. You can pretty much just use this, set it up as a system like this where you have a matrix equation, and then just use this general formula to find the general solution to the equation. And if you're given initial conditions, well, that makes it easier because you can actually solve for the values of the constants involved. So the initial conditions are usually going to be given in the form as a vector x of 0 equals to some set of values. So it could be something like 1, 2, 0 or something like that, and then you would just apply it once you have the general solution. Now, how do we go about solving this? Well, you know that to find the eigenvalues, what you need to do to matrix A is the following. You're going to find the determinant of the matrix A minus lambda of the identity matrix, which is just a diagonal matrix that has all elements 0 except for the diagonal, which is all ones, equals to 0. So you're going to solve this equation. So this is what we're going to do first. Once you find the eigenvalues, you're going to find the eigenvector that corresponds to each of those. So the eigenvector n. And once you have that, you can just plug it into here and then apply the initial conditions and you get your solution. So in the next video, I'm going to show you an example of how to use this. And then we're going to use this to set up a system of differential equations to solve a higher order differential equation.